So redox reactions are actually simultaneous reduction and oxidation reactions. The example given on top is one of the most basic reactions that we face in redox reactions. For example, we know that sodium and chlorine can react explosively together to form sodium chloride. Now, this is a balanced chemical equation for that reaction. And if you closely look, you know that the oxidation state on sodium is zero. The oxidation state on chlorine on the left side of the equation is also zero. But if you move to the right side of the equation, since that's an ionic compound formed by positive 1 ions of sodium, hence the valency +1, or negative 1 ions of chlorine, which we call chloride ions, hence -1 valency of chloride ions. So that's how we get the numbers on top. Now, we need to find which one is going through the oxidation process and which one is going through the reduction process. So it's pretty simple. Since sodium is moving from 0 to +1, it's going through oxidation because it's losing electrons. Chlorine, on the other hand, is gaining electrons and hence going through a reduction process. And that's how we depict it. We depict it with the help of two arrows, one drawn on the top of the reaction and one drawn at the bottom of the reaction. And vice versa, they are given with their respective names, oxidation and reduction. The first example at the bottom is of zinc and copper oxide. You can see zinc reacting with copper oxide, producing zinc oxide and copper. For this specific reaction, try to find out which exact element or compound or species is going under oxidation and which one is going through reduction. Go ahead.
For the zinc, it will be oxidation because it is gaining oxygen, and for copper, it will be reduction because it is losing oxygen.
But you're not doing it in terms of electrons. How would you explain in terms of electrons? Because gain and loss of oxygen is a question which is asked rarely in past exams. You're hardly going to see two questions about gain and loss of oxygen in past 10 years papers. How would you do it in terms of electron transfer? And they do mention the exact same phrase in the questions that I'm saying in terms of electron transfer. Then you're bound to answer in terms of electron transfer. You need to tell them which substance is losing electrons and how many electrons it lost, and which one is gaining electrons and how many electrons it gained. So yeah, you need to work it like that. That was a good try. You were perfectly correct. But if I asked you to go with a different perspective, what would you do? Go on.
Um,
Yes, can you understand or do you know how we find out the oxidation states, or how do we get to know that how many electrons are lost or gained?
no, sir, I don't really know that.
That's because the teachers not usually explain that. And to be honest, that's not even a part of the book either. That actually entices the students. Better yet, I should call the use the word entangle the students to a corner where they're not able to gain marks. So, were you actually able to go through the reduction oxidation part in those notes, types of reaction notes?
No, sir, I did it till rancidity.
Oh, now I got the point. So you do not know about reduction and oxidation parts, right?
Gee, I didn't go through the notes for
Okay.
this.
So I think we should stop it right here. We should actually go with those notes first and then practice after. Okay? So
Okay, sir.
we're gonna come back to this whole thing once we're done with those notes. So I'm going to stop sharing and I'm going to share the notes first. This means you went in the notes still far up ahead, like density, and the very next one was oxidation induction in terms of the types of reactions. And let me tell you, these are the last two types of reactions when we discuss about inorganic chemistry. Remember, these reactions entail only inorganic chemistry. They don't entail organic chemistry, and the type of reactions will be different in organic chemistry. In the part of organic chemistry, I mean. Okay. So let's move ahead. As soon as you're going to get to this page, you'll find a huge difference table. And this difference table is not just a difference table, instead, it's a collection of four different ways how we define oxidation and four different ways how we define reduction. So, one by one, we're going to define these ways, and I am going to then tell you which definition you're going to use when you're asked to define either oxidation or reduction in exams. So, let's get started. They are done in a table manner, the tabulated manner, because oxidation and reduction definitions are going to be exact opposite of one another. That's what makes them interesting as well as easier to remember. All right, let's get started. On your left, you have oxidation. On your right, you have reduction. The first way to define is addition of oxygen for oxidation and removal of oxygen as reduction, something you're already pretty familiar with. And as soon as you saw the zinc copper oxide reaction, you were immediately able to point point out that which one is going through oxidation and which one through reduction. So I hope you understand the first point already. Am I right?
Yes, sir.
Okay. The second, more unconventional point, a less used point, is removal of hydrogen or addition of hydrogen. In this case, removal of hydrogen is actually oxidation, as you can see on your left. The second way to define reduction would be addition of hydrogen. If in a substance we add hydrogen, we can easily say, if we say that it has been reduced. For example, in this case, nitrogen is added to hydrogen, and when hydrogen is added to nitrogen, it becomes ammonia, and we say that the nitrogen is reduced. Easy enough.
Yes, sir.
Okay, third and a very important definition, and let me tell you, whenever we go with the third definition, I always ask my students that this is the standard definition. So this is the way how you are supposed to define oxidation and reduction in exams when they're going to ask you define oxidation or define reduction in exams. So what is oxidation? To be honest, it is loss of electron or electrons, because you may lose one electron, you may lose two, you may lose three. So that really depends upon the type of element we're discussing. Like in this case, sodium can lose one electron and can easily form a Na positive ion. All right. So the exact opposite, gain of electrons, is the definition of reduction. As in this case, it has been shown that fluorine atom can give one electron to form a fluoride ion. Similarly, oxygen may gain two electrons to form an oxide ion. Both these cases are examples of reduction reaction. And since this is the standard definition, you are supposed to prefer this definition over any other definition. In the same way as oxidation, we may lose one or we may lose more than one electrons. In the similar way, we may gain one or we may gain more than one electrons. All right.
Yes, sir.
Next up is increase in oxidation state. Though this part can also be defined as loss of electron, but oxidation state, its increase or decrease is something that is important. Now, you may ask me the question that what is oxidation state? So let's just sit back for a while and let me tell you, as soon as I go with this point, of course, your question is right, and we need to explain what oxidation state is. So on the very next pages, you're going to find the definition and the entire explanation of oxidation state. So far, I'm going to keep it really easy and simple, somewhat straightforward as well. And that is, we can easily say that oxidation state is moved from a smaller valency number to a bigger valency number. Now, you do understand that plus 2 is a smaller number as per mathematics, and plus 3 is a bigger number. So moving from a smaller to a bigger number is increase in oxidation state, and that is stated as oxidation. Now, this is also considered as loss of an electron since we are losing one electron over here. But this change from plus 2 to plus 3 is what we are perceiving right now from it. Hence, the name increase in oxidation state. Oppositely, decrease in oxidation state would be known as reduction. This is pretty much the case of gain of an electron. But the perception is to move from plus 3 all the way to plus 2, which means a bigger number to a smaller number, and hence the term decrease in oxidation state. Make sense?
Ji, sir.
Okay, we are going to make more sense out of it once we define oxidation state and why this word is used. I casually replaced in some of the parts of my explanation this word with valency, but since we are dealing in ionic compounds, we can easily do so. Now, for apart from ionic compounds, since we are supposed to deal with both ionic compounds and covalent compounds in these cases, so we need to understand what oxidation state stands for. So let's move ahead and let's explain it. So on the next page, oh, before I move on, we have a mnemonic. This is actually a mnemonic. Mnemonic is a set of words or a collection of words that is commonly used to remember definitions or rules or important parts in the book. So actually, oil rig stands for oxidation, it stands for is, L stands for loss, and definitely we're talking about loss of electrons. In the similar way, R stands for reduction, I stands for is, G stands for gain, and I can assure you that you have already understood that it is gain of electrons we're talking about, right? So oil rig is a way to remember oxidation is loss of electrons and reduction is gain of electrons. Okay, this is
Yes,
also
sir.
given in your book. This is taken right out of the book. This is an old mnemonic. Every time we go visit oxidation reduction reactions, you're going to find it almost in every book, be it Cambridge's or Edexcel's or anyone's book. So what are redox reactions? Redox reactions are actually a simultaneous step of oxidation reduction reaction. In a single reaction, both oxidation and reduction occurs at the same time. We call it a redox reaction. In order to better understand redox reactions, oxidation state is something that we need to understand. So what is oxidation state? And the very words of apparent charge explain it all. Now, it's pretty easily understandable that for ionic compounds, their charges can be explained by valency. Sodium loses one electron, gets a plus one charge. Chlorine gains one electron, gains a minus one charge. So yeah, these are charges, and we have been using the word valency to explain them. But what if we are talking about a covalent compound? What if we're not talking about NaCl, we're talking about HCl? Now, HCl is a covalent compound. How would we know what kind of charges they do have? To be honest, covalent compound is formed by the sharing of electrons and they have no charge. Since they have no charge, that's why the term apparent charge. The charge is not actually present over there. Just for our own discussion or our own ease, we said this is the charge we give to them on atoms or on molecules or on species to simply understand them just the way we understand the ionic compounds. So this is a way to represent covalent compounds. Covalent compounds are formed by the sharing of electrons and not by loss or gain. So we use the word apparent charge. The charge in an ion is usually known as valency. In order to differentiate the charge, apparent charge is actually known as oxidation state. So oxidation state is actually a bigger, broader word. Valency is one of its types. Now, there are certain rules for assigning oxidation states to elements. The whole periodic table is filled up of elements. When you're going to make an ionic compound from a metal and a non-metal, it's pretty easy to come up with their charges of valency, right? But when you're dealing with only non-metals, and remember, covalent compounds are formed by a combination of non-metal with a non-metal. How are you going to give it charges then? You won't be able to until unless you have a set of rules how to work with it. So for those set of rules, let's start with the first rule. The first rule is this, that the periodic table groups have some specific charges. If we talk about ionic compounds, in case of ionic compounds, group 1 elements have plus 1 charge, group 2 elements have plus 2 charge, group 3 have plus 3 charge. Though group 4 elements don't exactly have a charge, but we sometimes can write plus 4 for it. Group 5 elements tend to gain 3 electrons, so minus 3 charge. Group 6 elements love to gain 2 electrons, so minus 2 charge. Group 7 elements love to gain 1 electron to become the electronic configuration of nearest noble gas, and a stable one at that. They are usually minus 1 charge. Group 8 is commonly known as zero because their oxidation state is zero. They don't like to lose electrons, they don't like to gain electrons, they don't like to share electrons either. Why? They're already stable and filled with electrons, hence zero state. So this is something that we need to remember commonly for ionic compounds. Let me tell you, nonmetals are capable of showing variable oxidation states. Why? Because they are capable of forming covalent bonds. So we're talking about group 4, group 5, group 6, and group 7. Apart from these, plus 4, minus 3, minus 2, minus 1, they will be able to show variable oxidation states. Why variable oxidation states? Because they can form different covalent bonds. Now you do understand, they may form a single covalent bond or a double covalent bond or even a triple covalent bond. So yeah, they are capable of showing variable oxidation states. Let's prove it. A couple of points before we actually try to prove it. So the next point, oxidation states for all transition elements are variable. We never know them. So what's going to happen is that in the paper, they are actually going to help you with it by giving a hint. What two kinds of hints that you usually get for transition elements? So for transition elements, the first kind of hint we usually get is the name itself. For example, they tell you iron to fluoride as a part of question statement. Now, from here, you know iron has what charge on it? This 2 easily tells you iron has a plus 2 charge. Make sense?
Yes, sir.
Good. The second way they're going to take it as is that they can give you a formula like this one. Now it's pretty easy. We can reverse multiply this number over here and this number right over here, which means iron has a 3 plus charge and oxygen has a 2 minus charge in this specific example. And we are done with this
Yes.
part too. You already know that cross multiplication, how that works, and vice versa, how reverse cross multiplication works, right?
Yes, sir.
Good. So these are the two ways. So they are never going to play unfair. They're never going to give you blind questions. Either they're going to give you the name and you're going to guess the oxidation state from it, or they're going to give you the formula. And of course, with a little bit of work of reverse cross multiplication, you'd know the charge on the transition element. So I think point number 2 is pretty understandable. Let's move to point number 3. The point number 3 is pretty simple and straightforward. Oxidation state for single element or single atom, for example, this is just single atom. What would be the oxidation state? 0. This is a single atom. Oxidation state 0. For atom, if for example, if an atom is uncombined with any other atom, its state is also going to be 0. This point actually links to the fourth point. Oxidation state for diatomic molecules such as hydrogen H2, fluorine S2, chlorine Cl2, bromine Br2, iodine I2, oxygen gas O2, nitrogen N2. These are all diatomic molecules. Diatomic molecules are the molecules which are made up of two atoms. In this case, two same atoms. Since they're same atoms, each of their oxidation states will be considered as zero. Why? Because though they have reacted and formed a molecule, but they are reacting under similar atoms. They never combine with any different atom. They combine with its own atoms. In that case, oxidation state is zero. So for anything apart from this, for example, the formula of ozone is O3. But since it only made bonds with oxygen atoms, or the oxidation state is zero. For example, phosphorus is usually present in the form of P4. Four phosphorus atoms combined together with covalent bonds. The oxidation state in this case, 0. Sulfur can form an S8 base structure. The oxidation case in this state, 0. Why? We still call it an uncombined atom. Why? Because it never tried to combine with any other atom. It combined within its own atoms. And that's totally fine. And the oxidation state in this case remains 0. Make sense?
Yes, sir.
So whenever you see uncombined atoms in an equation, give them the state zero. एक बहुत आसान टिप मैं बच्चों को बताता हूँ जीरो लिखने की, and that's going to be very straightforward. If in any formula, no matter how long the formula is, there is only one capital letter and no more than that, it will have the oxidation state of zero. All right. So whether the number is 2, whether the number is 4, whether the number is 8, this is made up of atoms and not ions. This does not have a charge. The oxidation state is going to be 0. Easy, right?
G, sir.
Okay, so far we had some easier points. Starting right from point number 5, we are definitely going to need practice. So I'm going to explain point number 5, and we're going to practice on the very next page. So oxidation for a state for a compound is equal to 0. Actually, what we are trying to say over here is given on the next page, sum of oxidation states of all the elements in a compound will be equal to 0. For example, NaCl is made up of sodium and chloride ion. Sodium ion has a charge of +1, chloride ion has a charge of -1. Right, two charges are on up top. Now, if you add these numbers, the answer would always be equal to 0,
Oh, right, sir.
right? But this is pretty much understandable since I took the example of an ionic compound. And every time I take the example of an ionic compound, the charges are going to cancel one another. But we are supposed to do the same with covalent compounds. Now, in case of covalent compounds, we might need to work it out. So I'm going to write a few questions right over here, and you can always work those questions to find out your answers. I'm just going to use a different color so that it does not combine with the blue and red, blue and black already given on the page. So fine, oxidation state, and you might want to grab a piece of paper and a pencil. Rough page and pencil would be perfectly good because you might need to write it down or solve it a little bit to give me my answers, because this is going to be an interactive exercise. So far was the explanation, that's why I was talking, but now you're going to solve it for me. Okay, though I'm going to explain a couple of questions first, but afterwards you are going to start solving them. So find oxidation state. Should we do it over here or should we do it on a whiteboard?
Sir, we can do it anywhere. It's fine for me.
Okay, okay. And do you have a copy and a pen ready?
Yes, sir.
Good. So find oxidation state of nitrogen, which I'm denoting with a capital N, in forming compounds. Now, since nitrogen is a non-metal, I will target only covalent compounds. Now, the key to solving this question is that the hydrogen will always have a state of +1. Sodium will also be +1. Potassium will also be +1. And oxygen is going to be -2 in all the upcoming questions. First question, NO. Now, since the rule says sum of oxidation states of all elements in a compound would be equal to 0, so we're going to use this. We already know oxygen is equal to -2 as stated over here. So oxygen is -2. What is nitrogen? We don't know. Let's put it as X. Now the solution says if I add, the word sum is right there, if I add this X and this -2, the answer would be equal to 0 right over here. So let's put it equal to 0. X minus 2 is equal to 0. In simple algebraic explanation, X is equal to +2, and X basically was nitrogen. So the answer to nitrogen is +2 in this case. That's how easy it is,
Oh,
right?
right. Yes, sir.
Okay, so I am going to go with some multiple compounds, doing like 20, 30 different questions for this practice makes my student perfect to find out any unknown oxidation state. So it's just the first example. I want you to go ahead with at least 10 to 20 different questions, and then you will be in a very good flow to solve any kind of question you're given with. Let's try and solve a different compound. This time we're going to solve something with different number of atoms. Since there were just one nitrogen and one oxygen atom, the previous question was very easy. This one is going to be a little bit different. Now, oxygen has a charge of -2. This time we're going to put it inside the bracket. Remember, charge is inside the bracket and outside the bracket, the number of atoms. Since there is 2 written over here, so I wrote this 2 over here. So we are supposed to multiply the charge with the number of atoms written in the subscript only. N is still x. We need to find it out. So it's x plus 2 into -2, which is equal to 0 as the whole rule says. So it's x minus 4 is equal to 0 and n, which is equal to x, in this case is equal to plus 4. So see, nitrogen in a covalently bonded compound with oxygen can show plus 2. A nitrogen in a covalently bonded compound of oxygen can also show plus 4. So yeah, nonmetals in covalent compounds are capable of showing variable oxidation states. And that's how we prove them by knowing that in a compound, the whole state is equal to 0. Why? Because the sum of oxidation states of all the elements will be equal to 0. And we are actually exploiting that rule to find out the unknown oxidation states. I hope that all makes sense to you, right?
Yes, sir.
Now let's try something even more difficult. Example number 3. This time, we're going to make sure that we have both the elements with different numbers, and if possible, prime numbers. How are we going to solve it then? We already know oxygen has a charge of -2, so inside the brackets, -2. Since there are 3 atoms of oxygen over here, there's 3 outside the bracket. We don't know the charge of N, but definitely what we know is that there are 2 nitrogen atoms this time, so 2x. Now, the equation must become 2x plus 3 into -2 is equal to 0. And if you know mathematical algebra, 2x would be equal to plus 6, and x would be equal to plus 3 in this case, which is equal to nitrogen. 6 is divided by 2, and the answer comes out to be plus 3. I hope you got that already, right?
Yes, sir.
Great. So now you understand. I have solved enough questions, so let's give you a question. Okay, so part number 4, N2O5. What's the oxidation state of nitrogen in this one? Part number 5, N2O4. Part number 6, N2O. Part number 7, KNO2. Part number 8, I will keep on writing the parts, keep on solving them. In the end, we're going to check your answers and make sure whether you're doing them right or not. So part number 8, NaNO3. Part number 9, NH3. Okay? I guess that's enough for the first question. So as soon as you solve a part and you have an answer for it, name the part first and then tell me your answer. For example, part 4, answer this, part 5, answer this, so on and so forth. Go ahead.
For part 4, my answer is 5.
Plus 5, that is correct. Well done. Moving on.
For part 5, my answer is plus 4.
Hmm? Really? Yeah, you are right. Yes, you're right. Good.
For 6, I am getting +6.
+6? How? It's just N2O. There's just one oxygen atom. How are you getting +6 out of it?
Um,
That's not right. Try it again.
and then +1.
That is right. +1. Good. Moving on. 7. Remember the keys
Okay.
written up top, and don't worry if you're getting a sodium ion or potassium ion in there or a hydrogen ion. It's always given above.
Is it +4?
+4. No, wait, no. You're missing out potassium in it. That's why you're
Mm,
getting the answer +4. Don't forget that potassium has +1 of its own, which is mentioned up top in the brackets. And I am going to mark it with a black pen right over here.
Sir, I'm still getting +4.
Now let me solve that out for you. You're talking about part 7, right?
Yes.
Okay, let's solve it. Potassium, as we know, is +1. Oxygen, as we know, is -2. But there are two atoms of oxygen, so two outside the bracket. Let's put N as X. So it's +1 plus X plus 2 into -2. So the whole of it is +1 plus X minus 4 is equal to 0. I've got to put it equal to 0. And from here on onwards, it's actually X is equal to 4 minus 1, and that is equal to +3. How come you are getting a different answer?
Oh,
You must not be using potassium in there, right?
yeah.
Okay, good.
For the 8 part, I am getting positive 5 plus 5.
Perfect. Let's move on to 9.
For the last part, is it -3?
-3. Perfect. Now, I hope all the answers are in front of you. So let me give you a quick revision. This one is +2, +4, +3, +5, +4, +1, +3, +5, and then -3. Can you see how many different states a single nonmetal nitrogen can show with just a couple of metals and nonmetals in different types of bonding, right?
Yes.
It can give you a very good idea how that works. Now, since we are at it, let's practice a little bit more. And the rules are pretty much the same. I am just going to raise a few parts at the bottom. I'm not going to raise the key. I'm going to keep the key as such so that you can use it for the further set of questions, right? And I don't think I need to explain anything anymore since you're already good with it, okay? So let's change it a little bit. This time, we are going to talk about sulfur. So part 1, SO2, sulfur dioxide, a common gas we're familiar with. Part 2, SO3. Part 3, Na2SO4. Part 4, H2S. Part 5, KHSO4. Part 6, Na2S2O3. And finally, part 7, Na2S2O7. So let's find out how many different states is sulfur capable of showing in these different options.
For the first one, it is +4, +4, and for the
Good.
second one, it is +6.
Perfect. Okay. Now let's not waste any more time in solving all of these. Just write the questions and take them as a homework. Solve them if you face difficulty with the stuff coming up. But if you don't face any difficulty, I already understand that you know how to solve it, right? So
Okay,
even
sir.
if you do it at home or even if you do it with me, we both have understood the fact that you are going to get them correct, right? So at least we know this kind
Yes,
of
sir.
question, a rebar ox. Okay. So let's move on. All right. So since you know the rules, the next part is going to be extremely easy. In case of oxidation state, for anion, it's not an anion. There is a space in between. It's anion is equal to its charge. So it's a similar case. Just that in case of ion, the charge would be equal and it would not be equal to 0. Let me clarify with a set of questions. Find oxidation states of, okay. And the key is similar to the previous question. Since you already have the key noted down from the previous question, it shouldn't be a problem. You noted down the key, right?
Yes, sir.
Okay. So number 1, N in NO3 negative. Number 2, S in SO4 2 negative. Number 3, P in CO4, 3 negative, and finally, number 4, C in HCO3 negative. Now, in this case, what are you supposed to do? Let me explain one. Nitrate is equal to negative. So that means oxygen is -2 and there are 3 atoms for it. Nitrogen is X. So the equation becomes X plus 3 into -2. And this time it's not going to be equal to 0. This time it's going to be equal to the charge. So -1. So every time for every ion, the equation is equal to a different number. For nitrate, it's minus. For sulfate, it's -2. For phosphate, it's -3. For hydrogen carbonate, it's -1, right? So it is going to be equated to
Yes,
something
sir.
different. It is going to be equated to equal to the charge on the ion. Try going with this question and let me know what the answer is. I've already solved the first step of it. Then after doing part 1, don't jump on to part 2. Directly move on to part 3. I specifically want you to solve part 3 first. So the answer to part 1 is
+5 plus
perfect.
5.
Perfect. Now after solving part 3, let me know whether the part 3 has the same answer or a different one.
It is coming same for the third one as
Right, very good. If it's same, it's correct. Both nitrogen and NO3 negative nitrate ions and phosphorus in phosphate PO4 negative free ions has the same oxidation state +5. All right. Since these notes are written by a student and not by me, so there are many mistakes. So let's cut out this part. Instead of this part, I want you to note something else. Okay, this is something old. Let's get on with the updates. So hydrogen. In case of hydrogen, most compounds, the state of hydrogen would be equal to +1. Only in the case of hydrides, and when their name is mentioned as hydrides, the state of hydrogen would be -1. Let's talk about oxygen. In most of the oxides, hydrogen, the state of, sorry, I keep mixing up the words. In most of the cases, oxides would have a state of -2, but only if the name of the compound is peroxide, the state of oxygen would be -1. Lastly, something most important and something most particular in the whole periodic table is fluorine, which is always -1. All right.
yes.
When you're done writing these three, let me know. I'm going to clear everything and I'm going to move on.
Done, sir.
Good. Now, moving on. Um, Now, redox reactions are simultaneous oxidation reduction reactions. Now, take a look at this. Remember the rules. Diatomic molecule, 0. Oxygen, uncombined with any other atom, 0. Water, oxygen is -2, hydrogen is +1 into 2. So take a look. Hydrogen is changing from 0 all the way to +1 over here, and oxygen is changing from 0 all the way to -2 over here. Now, how do we know this is oxidation or reduction? Let's go a few pages back. We defined it already, but I am just going to joggle your memory a little bit. Now, remember, increase in oxidation state going from a smaller number to a bigger number is known as oxidation. Vice versa, going from a bigger number to a smaller number, which we call in decrease in oxidation state, was taken as reduction. So it's pretty simple. If mathematically we are moving from a smaller to a bigger number, oxidation, and bigger to a smaller number, which means vice versa, of course, reduction. So 0 and +1. Of course, 0 is a smaller number, +1 is a bigger number, hence that is oxidation. 0 and this one is -2. So if we're going from 0 to -2, we know 0 is a bigger number in math as compared to -2. So it's going moving from a bigger number to a smaller number, hence reduction. Make sense?
Yes, sir.
Now, the equation that I started off with in the Microsoft whiteboard at the start of this class was all about these equations. Let's do another example equation, a similar one. So we know that metals can react with oxygen. So sodium reacts with oxygen, 0, 0, +1, -2, and all the states are written. Now, sodium is going through the process of oxidation because 0 to +1 is from a smaller to a bigger number. Oxygen, on the other hand, is going through reduction. Why? Because it is moving from 0 to -2. And this is the way how we represent it. One arrow up top of the equation, be it oxidation or reduction. One arrow at the bottom of the equation, be it oxidation or reduction. Remember, the arrow starts from the same element and ends at the same element. Make sense?
Yes, sir.
So next up, magnesium and oxygen, almost a similar reaction. Now these are pretty easy reactions. These are what we call baby steps because these are ionic equations. A metal reacting with a non-metal forming an ionic compound, and you always know metal loses the electrons. So of course it's going to go through oxidation. Non-metal gains the electron. So of course it's going to go through reduction. So these are very easier equations. And to be honest, they never come as a part of exam because they're too easy to solve. In exams, what they do is that they discuss something comparative, a metal with a metal or a non-metal with a non-metal. In that case, you won't be able to guess simply that a metal loses electrons and a non-metal gains them. So example number 3, pretty easy. Example number 4 is something that we already did, pretty easy. Example number 5 is easy. Again, a metal and a non-metal. Mostly it's oxygen in case of non-metal. So is example 6. But if we talk about example 7, now this one's interesting. Both nitrogen and hydrogen are non-metals. How would we know that which one exactly is going to lose electrons and which one is going to gain electrons? Now, this is only going to be right if you calculate the oxidation states. There is nothing to calculate in this one. This one is of course 0, nothing to calculate in this one either. This one is also 0. We do not use these numbers in any multiplication addition in this case, neither this one. So this one is -3. The student have made a mistake over here. It's not 3, it's actually 3 into +1. So hydrogen is moving from 3 to +1, hence oxidation. This time it all changed. We were continuously writing oxidation up top and reduction at the bottom. Now, this one is from 0 to -3, and -3 is, of course, a smaller number, hence reduction. All right. Last
Sir, but
page.
how
Huh?
do we know that it's -3? Like the method we did right now.
Yeah,
We will do that?
you just solved ammonia a few moments ago. आपने अभी भी NH3 solve किया है. It was the last part of
जी.
nitrogen questions.
जी. Okay.
Yeah, that's good enough. So that's how you know. These
Okay,
equations,
sir.
देखें, एक कंपाउंड नहीं आता. एक कंपाउंड तो बच्चों वाली बात है. वो एक कंपाउंड में एक अननोन एलिमेंट हो, बच्चा फौरन फटाफट 2 स्टेप करो, उसको 5 नंबर मिल जाए. ये नर्सरी का गेम थोड़ी है ना. We were talking about O levels, of course. So giving you an entire equation means you need to solve this compound, you need to solve this compound, you need to solve a couple of more compounds, and then there is element with zero, and then you need to find out what's right or wrong with it. Okay, giving you just one
Right.
compound is like spoon feeding you the marks. Of course, everyone would be able to do it correctly, and everyone would be able to get an A. They're not distributing A's to the students, they are actually testing them. Okay, I'm going to use this equation, but not on the same space since it's solved over here. So let's do it on a different space. Okay, this equation is iron oxide is capable of reacting with oxygen and producing this iron oxide. Now we have an iron oxide on left, we have an iron oxide on right. We know iron is a transition element and we don't yet know what its state is. Though we know about oxygen that oxygen is zero in terms of diatomic molecule, but when it's combined, it's -2 as an oxide. So of course, if we solve it for x, you will find out that the value of x in this case turns out to be +2. You can solve it later and you'll find out this is +2. Now, if I solve this one, this is -2 for oxygen, and I know there are 3 atoms. If I solve it for x, and of course there are 2 atoms, I'll put it as 2x. The whole answer will come out to be something like this. Sorry, I'm going to erase it. I'm going to rewrite in the same space. That's going to be 2 into +3. +3 is the charge, and 2 is the number of atoms. Okay. So now, notice iron is going from +2 to +3. Only the numbers inside the bracket says that's the oxidation state. Number outside is simply the number of atoms, and we don't need to talk about it. Now, oxygen is present over here as -2, over here as 0, and over here as -2. If I use this arrow, this would be wrong. If I use this arrow, this would be correct. Why? Because we are moving from 0 to -2. 0 to -2 is reduction, and +2 to +3 is oxidation. Since smaller to bigger or bigger to smaller numbers, what defines oxidation and reduction? Make sense?
Yes, sir.
Good. A few more equations of practice, and you'll be good with oxidation reduction equations. And that is one of the most important questions out of question chapter number 4. All right.
Yes, sir.
Good, good. We are going to do the next part and we are going to prepare them before you test. When is your test due, by the way?
It is on Monday.